Welcome to Organic Chemistry. Unlike IR spectroscopy, which has told us about bond vibrations and functional groups, NMR gives us direct insight into electronic environments surrounding nuclei within a given molecule. In many ways, NMR is less about identifying atoms themselves and more about understanding how molecular structure redistributes electron density throughout a system. Let's get started. At the expense of condensing so much information into one slide, we cover the fundamental principles of NMR. Certain nuclei behave like tiny magnets because they possess spin, just like electrons. When we place those nuclei into a strong external magnetic field, they can align in different energy states, some with the magnetic field, some against the magnetic field. Radio waves can then induce transitions between those lower and higher energy states. However, the nuclei in their spins are not isolated. The surrounding electrons also respond to the external magnetic field by generating local magnetic fields that can work with or partially oppose it. This means nuclei experience different effective magnetic fields depending on their molecular environment. If a nucleus is highly shielded by electron density, it experiences a smaller effective magnetic field and requires a lower resonance frequency in order to make that transition. If a nucleus is de-shielded, it experiences a stronger effective magnetic field and requires a higher resonance frequency to make that transition. This ultimately produces the chemical shifts we observe in NMR spectra. So, NMR does not directly identify atoms, it identifies how molecular electronic structure alters the magnetic environments experienced by those nuclei. Now, the first major idea in carbon NMR is that the number of peaks correspond to the number of unique carbon environments. Equivalent carbons generate the same signal because they experience the same electronic environment. As we move from simple sp3 carbons into more delocalized systems, the electronic environment changes dramatically. Notice that sp carbons appear further downfield than sp3 carbons. The electron density associated with pi systems is more delocalized than in purely sigma bonded systems and thus alter shielding behavior. For sp2 systems, the effect becomes even greater due to anisotropy associated with planar high molecular orbitals. Aromatic systems take this even further. When an external magnetic field is applied to an aromatic ring, the circulating pi electrons generate a secondary magnetic field. Outside the ring, nuclei become substantially de-shielded, pushing aromatic signals downfield. And inside the ring, nuclei would actually become more shielded. This is one of the most clear examples that molecular geometry and electron delocalization directly influence magnetic behavior. Electronegative atoms withdraw electron density through sigma bonds, de-shielding nearby nuclei. The closer a carbon is to the electronegative atom, the stronger the effect. The alpha carbon, the carbon directly attached to the heteroatom, experiences the greatest de-shielding. Beta carbons are affected less strongly. Notice how fluorine produces an especially dramatic effect due to its extremely high electronegativity. Larger, more polarizable atoms like iodine distribute electron density more diffusely, so the de-shielding effect is less localized. This is important because NMR chemical shifts are fundamentally sensitive to how electron density is distributed spatially throughout a molecule. So, first, we count the number of unique carbon environments. Then we ask, what kinds of carbons do those environments represent? Carbonyl carbons appear strongly downfield because the pi system and electronegative oxygen substantially deshield the carbon nucleus. Aromatic carbons clustered together in characteristic regions due to aromatic anisotropy and delocalization. sp3 carbons bonded only to carbon and hydrogen appear much further upfield because they are comparatively shielded. sp3 carbons attached to heteroatoms shift somewhat downfield due to inductive withdrawal of electron density. Here, the goal is not to memorize isolated values, but to learn to interpret spectra as consequences of molecular electronic structure. So, this is the workflow for interpreting carbon NMR spectra. First, we count the peaks. The number of peaks equals the number of unique carbon environments. Next, we identify major highly deshielded regions. Carbonyls appear furthest downfield. Unsaturated carbons occupy intermediate regions due to pi electron effects and anisotropy. Carbons attached to heteroatoms appear somewhat downfield relative to simple alkyl carbons. And finally, ordinary alkyl carbons occupy the most shielded region of the spectrum. Notice the general trend. Greater deshielding corresponds to lower electron density and larger ppm values. Greater shielding corresponds to higher electron density and smaller ppm values. The entire spectrum is essentially a map of electronic environments. Now, proton NMR follows the same fundamental shielding and de-shielding principles as carbon NMR. However, proton and spectra contain additional information because neighboring hydrogen nuclei can magnetically influence one another. This produces signal splitting. Each neighboring nucleus may align either with or against the external magnetic field, slightly altering the effective field experienced by adjacent nuclei. The result is splitting into multiple peaks according to the n+1 rule. Equivalent neighboring hydrogens generate predictable splitting patterns, as described by Pascal's triangle. However, the n+1 rule only works cleanly when neighboring hydrogens are equivalent and sufficiently separated in chemical shift. Notice how anisotropy again influences proton shifts. Alkynes appear more shielded than expected because cylindrical pi electron circulation partially shields the proton. Alkenes in our aromatic systems instead strongly deshield nearby hydrogens due to planar anisotropy and aromatic ring currents. As always, the electronic structure governs the magnetic environment. In proton NMR, the area under the signal provides the relative ratio of hydrogens present in that environment. This process is called, of course, integration. The integrals themselves are relative and not absolute. For example, the 6:2 ratio simplifies to 3:1. Integration therefore tells us how many hydrogens are contributing to a given signal relative to the others in the spectrum. This becomes incredibly powerful when combined with chemical shift and splitting information. So now we combine all of the major proton NMR ideas together. First, we determine the number of unique proton environments. Second, determine the relative number of hydrogens in each environment using integration. And third, identify the types of environments based upon chemical shift. Only after that should splitting be used to determine connectivity between neighboring groups. This order matters tremendously. Students often overfocus on splittering patterns too early and lose the broader structural picture. Notice again how electronegative atoms shift nearby proton signals downfield. Broad exchangeable peaks from alcohols and amines may or may not couple depending on exchange conditions. NMR interpretation is therefore not just pattern recognition, it is interpretation of electron structure and molecular dynamics. So, the general workflow for interpreting proton NMR spectra is as follows. First, we count the signals. Each signal corresponds to a unique hydrogen environment. Second, use integration to determine the relative number of hydrogens contributing to each signal. Third, identify highly characteristic regions. Carboxylic acid and aldehydic protons appear furthest downfield due to extreme deshielding. Aromatic and vinylic hydrogens occupy intermediate deshielded regions because of pi and isotropy. Hydrogens attached to or adjacent to heteroatoms shift downfield due to electronegativity effects. Ordinary alkyl hydrogens remain the most shielded. Finally, splitting reveals neighboring connectivity. Again, the spectrum is not arbitrary. Every shift emerges from how molecular structure redistributes electron density and alters local magnetic environments. And that wraps up our last video from Organic 1 and 2, at least for this year. Till next time, Crip.